Okay, so today we're going to talk about electrons, specifically the importance of electrons and how they are used as we are leading into chemical bonding. First thing we're going to do is look through a couple of models. Um, a model should just explain um, not just what the material is made of, as in the composition, but it's also going to possibly explain how it behaves as to the changes it undergoes. So we're going to look at a couple of models here that have historically been present and historically have helped us come to a better understanding of what's going on with the electrons and why electrons are so dearly important in the world of chemistry. If you recall, we had three what we call subatomic particles. Those subatomic particles were protons, neutrons, and electrons. And also earlier this semester, you'll recall that we went over charges. We went over how to calculate those totals. We called those PEN numbers, P-E-N. And so protons, if you'll recall, have a positive charge. Neutrons have a neutral charge. And electrons, therefore, would have a negative charge. So we're looking here at model. And let me see if I can make this go into projection mode here. There we go. So models of the atom. Um, there was a man named Ernest Rutherford who developed a atomic model early on. However, his model was incomplete, gave us some good starts, but was incomplete because he could not explain the chemical properties of the elements. And so basically couldn't tell us why things would change color when heated or why light was given off, those type of things in reactions. All right, see if I can go forward here. Okay, so the atomic model of the timeline uh, goes as follows. Back in 1803, you had John Dalton, and Dalton's model basically said that atoms were this tiny, solid, spherical shape, right? They were indestructible, no internal structure. We move on about 90 years roughly, and you have J.J. Thomson's model. He came up with a model called the plum pudding model that basically said that electrons were inside the sphere that Dalton had mentioned. You had these little negatively charged particles that floated around that sphere. And some people have referred to this also as the cookie dough model or the chocolate chip cookie model, because if you notice, it kind of looks like a chocolate chip cookie. Moving on, then we get into 1911. New Zealand physicist Ernest Rutherford finds that the atom has small, dense, positively charged nucleus, and the electrons move around that nucleus. So Rutherford basically gave us the idea of a nucleus. Prior to that, in J.J. Thomson and in Dalton's model, neither one of them said that we have a nucleus. So now with Rutherford's information coming forward, we do have a nucleus, and that nucleus we said was small and dense and positively charged. Therefore, all of the area surrounding the nucleus to the outside would be considered the electron area, right? So those electrons then, which we said were negatively charged, would move around the nucleus, which is positively charged. Move on here. In 1913, you had Bohr. Niels Bohr came in and gave the electron moves in a circular orbit. So now we have a fixed frame of reference here, right? They're going to go in orbits. So much like the planets move around or revolve in orbits, Bohr said that the electrons do the same, right? And notice that an electron up there says it can gain or lose energy by changing its orbit. That's going to be important later. So hang on to that bit of information. We're going to skip forward a little bit more through the years. You had Schrodinger, right? Schrodinger came in and gave us a mathematical equation to describe the motion of electrons and atoms, and his work leads us to what we call the electron cloud model. And so if you notice in the diagram there, The electron cloud is a visual model of the probable locations of electrons in an atom. Now notice we say probable. We say probable because they move so quick, right, that by the time it took you to pinpoint one electron, it would have already moved, right? So we say probability. So the probability of finding an electron is higher in the denser regions of the cloud. And we'll talk more about this cloud. We'll talk more about gaining and losing energy in its orbit, and how that happens, and what the ramifications of those are, right? Notice also in this timeline in 1932, you had James Chadwick that confirms the existence of the neutrons that have no charge, and the atomic nuclei contain neutrons and positively charged protons. So 1932, what we have is Chadwick comes back together and confirms not only that there is a nucleus, but now that there is two particles, or two subatomic particles, in the nucleus. And those two subatomic particles would therefore be the positively charged protons and the neutral neutrons, right? They're going to be in the nucleus. That leaves the outside area, the area in red here around your green and purple, right? That area of pink or red would be the electron cloud, right? Very important to know that as we move forward. So again, we talked about Bohr. Bohr introduced his atomic model based on the simplest atom. He really only has studied and looked at hydrogen, which we all know only has one electron, right? It's up there by itself. Bohr proposed that an electron is found only in specific circular paths or orbits around the nucleus. This is somewhat true, somewhat untrue, and we'll look at that more closely. But important to know that Bohr started the frame of reference here. So if you look here, we've talked about ground states and we've talked about excited states, and Bohr was one of the first ones to kind of diagram this out. But if you notice, you've got your nucleus, which we said was your positively charged material, and your neutrons, which are neutral. And then you've got your electron, which is outside of that nucleus, and the electron is negatively charged. In the ground state, the electron wants to be as close to the nucleus as possible, right? We call that the ground state. It's in a more relaxed state. They use the example in the past that, you and I, if we had the option of remaining home every day and sitting and watching TV, eating a bowl of Cheetos, right? That's probably what we would take, because it requires less energy of us, right? It requires us to be in what we call our ground state, right? At home, relaxed, where you want to be. However, Bohr said that those electrons can actually change or move orbits. So then we become introduced to what we call the excited state. So now if you notice, the electron has moved out further away from the nucleus, right? Further away from the nucleus. So now the electron is in an excited state. It has, in effect, had to get up and get dressed and go to school that day, right? You're further away from home here in school than you were when you woke up this morning. So that is its excited state. So the electron is now excited and pushed out further away from the nucleus. So we say that each electron has a fixed energy level, right? And the electrons can jump from one of those levels to another. However, the electrons cannot exist between energy levels. So they have to either be in level 1 or level 2. There is no level 1.5, right? Or level 1.5. And so we call this energy, we call this a quantum, right? In red here, you see the word quantum. A quantum of energy is the amount of energy needed to move an electron from one energy level to another, right? And so we start looking at quantum energy levels. That's the energy it requires to move an electron from one level to another level. Okay, that's going to become important. And all of this leads to chemical bonding, which we're going to take a look at and we were introduced to through the pumpkin experiment where we exploded our pumpkins. So here you see n levels, right? Those n equals 1, equals 2, n equals 3. Those are our quantum numbers. And so n equals 1 would be the one that's closest to the nucleus, right? And we'll talk more about this, but you've got movement here that can happen with n equals 1, n equals 2, n equals 3, right? And so that's important to note. So keep your eye on that. The degree to which they move from level to level determines the frequency or light they give off. So now you see frequency here, right? Frequency A, if you're going to move from energy level 3 down to energy level 2, then you can get a red light given off, right? A reddish cast. If you're going to go from 2 down to 1, you're going to get a green light or a green cast given off in the reaction. Or if you go from level 3 all the way down to level 1, right, then you're going to get a bluish cast or blue light given off. So that's important to note, that light occurs because the electrons are moving through energy levels. Okay, and you probably never heard that before, but that is certainly true, that light is emitted because the electrons are changing through their energy levels, right? They're being excited or they're being de-excited, if you will, or unexcited. So they're either moving closer to the nucleus or they're moving further away from the nucleus. And the degree at which that happens will emit certain frequencies, which cause us to see certain colors, right? So that's very interesting for us to note. To move from one level to another, the electron must gain or lose the right amount of energy. The higher the energy level, the further away from the nucleus it will move, right? And so you're going to gain energy to move to a higher energy level. That means you're going to move away from the nucleus. Or you're going to lose energy to move to a lower energy level, which is going to put you closer to the nucleus. And either way, whether you gain or whether you lose, and the amount you gain or lose will respond to a certain frequency, which responds to a certain color that you're going to see. Okay, let's move on. The amount of energy required to go from one energy level to another is not the same for all the electrons. Higher energy levels are closer together, right? This means that it takes less energy to change levels in the higher energy levels. So if you look over here at the ladder to your right, all right, if you notice the rungs of that ladder, the rungs towards the ground are spaced further apart. So the very first rung that you see, right, is more space between the ground and the first rung than it does the first rung to the second rung. So as you climb that ladder and get higher in the number of rungs that you see, the rungs actually get closer and closer together. So if you look up, if you're counting your rungs, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 rungs on this ladder. When you start reaching level 5 and beyond, the rungs move closer and closer together. So that by the time you get to rung level 8 and 9, they are really close. So it doesn't take as much energy to move one from level 8 to level 9 because they are fairly close together. However, if you go back and look at rung level 1 and 2, right, it takes a great deal of energy to move it from level 1 to level 2, right? And then it takes even less energy to move it from 2 to 3 and so on and so forth, right? And so that's important to note, and that certainly still holds true today. But the Bohr model was tested with just hydrogen. Remember, it just had one electron, but failed to explain the energy levels absorbed and emitted by atoms with more than one electron, because he didn't look at anything but hydrogen, right? So we need to expand and understand, more about the other elements, because obviously not all of them are going to contain just one. So when atoms absorb energy, electrons move into higher energy levels. These electrons then lose energy by emitting light when they return to lower energy levels. So if you look at Mercury, right? Mercury, you see a blue, which we discussed in this frequency earlier. Nitrogen, you see more of a pink, right? And so that we know that as atoms absorbs the energy, they're going to move into higher energy